Welcome to Moody Coda. My name is Mike Moody, and this is a channel where I share tips, tricks, and just general advanced knowledge that I've acquired over 8+ years of working as a ServiceNow developer. I started off working for a managed service provider, and today I work as a primary architect and developer team lead at eBay. And so today it is my desire and hope to impart to you some advanced knowledge that I've acquired through trial and error, experimentation, to deal with handling the processing of a large number of events and slow event processing as well. I use this technique today to handle over 400,000 transactions per week. Some slow, some fast. This is a very optimal way, I think, personally, I feel, of being able to deal with processing large amounts of transactions without detrimental impact or effect to the system as a whole. So hopefully, you'll agree with that after watching this video, and you'll get something useful out of this. That is my hope, and to be able to share this knowledge. So I title this Optimizing Slow and Heavy System Event Processing at Scale. So this is actually meant to be sort of an extension. I'm actually going to leverage the solution that I built in the last video, which was titled High Throughput Asynchronous Integration Handling using the REST message version 2 with custom callback functions. So I'm going to extend on that implementation to set the stage for dealing with slow processing in those responses, and then show you how you can alleviate the pressure on the system when dealing with such a scenario. So let me go ahead and get started. Now, before I start digging into code, I actually want to take a minute to talk about some concepts here. So really, our optimization goals is what's of importance here. What we want to do is we want to maximize the use of available instance processing resources. Sounds like a good thing. Yes, of course, let's do that. The second thing we want to do is to protect our available instance nodes from event queue backups. And this is critically important right here, because it's one thing to try to maximize your performance and the utilization of the resource, is another to protect them from being overutilized to the point of rendering the system inoperative or rendering critical events from being able to do what they need to do, essentially run. All right. So what I want to talk about first is I want to talk about how events are handled within the system. So if we look at a single node in the ServiceNow instance, you will find that a single node actually has a total of 8 worker threads. These threads run in the background on the node server, and they're responsible for checking the sys_trigger or the scheduled jobs table to find a job that the worker can pick up and execute on that background node, right? So at any given moment in time, each of these 8 workers can either be idle, as we see with worker 0 here in this image, or can be processing a job, as we see with worker 1 at any given point in time. Okay, so there are a couple of there are multiple ways of generating these scheduled jobs. You can create them by hand. They can be created as a result of having been inserted to the table programmatically by the system from another type of record, like the other scheduled job type record that you set up for recurrence. Yes, and even, believe it or not, these are automatically inserted by the system when asynchronous business rules are run. And this is of interest. We left off on the last video where I was showing how to implement an asynchronous business rule on the ECCQ table in order to handle asynchronous responses and call a callback function on reception of those responses. So let's talk a little bit about the asynchronous business rules. But before I get into this too much, I want to switch to my personal developer instance and give a little demo as what happens with asynchronous business rules when you encounter slow processing performance that they're responsible for executing. So from the last video, what I had done is I implemented a script include called integration util, and this has just two functions: a get function, which does an API call to my personal dev instance in order to emulate a remote system. And when I implemented this, the intent was for a slow running call, so the remote system would take 20 seconds before it would respond. Sort of emphasizing the usefulness of the asynchronous calls, where you can just fire and forget and wait for that response to come back. Now, in this use case, in this scenario, the callback function is down here. This is the second function in this script include. And what I'm going to do in this use case is I'm actually going to add the delay in the callback function. So now I'm inducing a 20-second delay when it's processing that response internally in the system here. So that means that when this asynchronous business rule triggers that callback function, which is this one here, it's going to be experiencing with each call a 20-second delay. All right, so now let's see what happens when I do a test with this and I trigger 200 API calls against this endpoint, and let's see what happens to the system. Now, before I do this, I do want to show one thing, is I have a screen here, a system diagnostics page, where I'm able to show the current state of all 8 workers that exist on this instance node. Currently, they're saying that they're idle, and I got a refresh button here. I can check, and they're still idle. So now we know they're idle. They're sitting there. Now let me go ahead and kick this off. I'm going to send 200 API calls to my endpoint, and since this is running asynchronously, it's already done creating those records. So now those calls should be running behind the scenes. So let's keep an eye on this list of workers and see what happens. Aha, look at this. So all of the workers are being consumed with running the asynchronous business rule. So as you can see, what the system's doing when it hits an asynchronous business rule is it actually inserts a record into the sys_trigger table with this prefix of async and the name of the business rule, and it executes it. And as you can see here, since I fired 200 calls and each one of those in processing is taking over around 20 seconds to process, it's filling up all of the workers. And it's also tying up the workers because as each one of these is consuming 20 seconds worth of time, they're not available to process any other events in the system. And this can, cause some serious issues with, it can cause workflows to be delayed. It can cause other critical system functions to be significantly delayed if they're sitting here being tied up by a slow processing job. And of course, the slower the job, the longer that worker thread is tied up. So here we are, we're all backed up here. I mean, keep refreshing and keep an eye on this thing. Now look at this. So now our scheduler queue length has gone red because we're starting to accumulate more events in the backlog than the system's able to process, because all these workers, again, are tied up processing these asynchronous jobs. So this is the problem with asynchronous jobs. And I'm going to switch back and walk through this. So basically, what we learned from this demo is that a pros of the asynchronous business rule is that it can run on any worker on the node, which is actually, a good thing because, and then multiple instances of the same job can run simultaneously across multiple workers, which is what we're seeing. So that same business rule is running, 8 different times, it's handling 8 at a time, but it's also the problem that introduces is that there's no control to limit the number of workers that are consumed at once. So as we saw, it's tying up all of the instance resources to process these business rules, right? And then it's the slow processing code. It can tie up the workers and delay other critical events. So those are the cons of async business rules. So how do we address this issue? How do we solve this problem? What other options do we have? Well, the other option that we have is the use of custom event queues. Yes, and with custom event queues, we can limit the total number of workers consumed at a single moment in time. We can also scale jobs across multiple workers, similar to how the async business rule is doing. And then beyond that, we can actually scale the jobs across multiple instance nodes as well. The cons of this approach, well, it takes some advanced setup to get it right, and it requires some sort of scripted mechanism to control the event to queue distribution. If you want to send an event to a specific queue, you need to have some sort of control to be able to have that logic in place, okay? So I'm going to go ahead and show you how to build out a custom event queue approach to handle this use case and get a little bit more control over the system and the impact on the system when you're doing something like this. All right, so let me switch back here, and first thing I want to do is stop the system from processing these, and so I can free the resources back up. So I'm going to go to the events table, and actually, let's see. No, not the events table. I'm just going to go and look up the transactions running on across all nodes here and find those async business rule transactions. Yes. So actually what I should do is look in our schedule here for anything with async. So Y and C. And here we go. Async integration sensor. Here we are. So these are the guys, the business rules that are running. So I want to kill these guys. Let me delete these first of all. Delete those. Yeah, let's do it again. So I can clear out the backlog. There's 175 of these, it looks like here. And this is kind of the slow way of doing it, it would seem. Yeah, probably don't want to do that 10 at a time. So yeah, let's show matching on this. All right, let me go ahead and just copy this query. And I think I got a bit of code here real quick to delete this. So var query equals, and I'm deleting from the systrigger table. All right, so let's do a count on it first of all. Let me just duplicate this. All right, let me run a count on that and make sure we got the right number. So there's 45 in there at the moment. And then let's go ahead and delete those. Run. Security restricted. Gonna have to switch to global and run that again. Okay, there we go. 45 deleted. Now the other thing we want to do is go to the running transactions on all nodes and kill any still running transactions related to those async jobs. It doesn't look like I have any, so it looks like I successfully stopped them from running. Yep, I don't see that anymore. Then if we can double check by checking our diagnostics page here. Let's refresh. Yes, so our schedulers are now idle again. Okay, so now let me go ahead and go to the studio environment here and and make some adjustments to our business rule and implement some other records so that we can actually do a custom event queue approach to this issue. So the first thing you want to do is create a new event registry record. So I've already gone ahead and done that for this. So I created a new event registration record called callback. So this is going to be the event that is going to be triggered in lieu of using an asynchronous business rule, or I should say, to do the heavy lifting coding, I'll be triggering this. So this is going to be fired by the existing async business rule on the ECCQ table, and it's going to execute the callback function on the async response, right? So essentially, we're just going to take and forklift this code in here that's doing the callback function, and we're going to put it into a script action that's going to be triggered by this event. So that's the first step, is creating this event. Second step is creating that script action I just spoke of. So here's a script action that I created called process async callback, okay? And then I have a simple function in here, is passing in the current glide record, which is the ECCQ record. And then this is the same code that I had that was doing the callback function directly in the asynchronous business rule. Now it's being done in a script action, right? Okay. So with those two things in place, the last thing to do is to create a custom queue processor, okay? So in order to do this, we want to go to the scheduled scheduled jobs table. Of course, there are multiple scheduled jobs table, as you'll notice when you search it up in the left nav. The one that we care about, or the one that we want in this particular case, is the one down below system scheduler. Now, this is the one that is the sys underscore trigger table. I spoke about it before. And here, you just want to do a search for a event, or I'm sorry, not an event, but a scheduled trigger that contains the word text index, right? So we do a search for that. And this is a text index event processor. So we want to create a record similar to this one, only instead of processing events that are dropped into a queue titled text underscore index, we want to process events dropped into a queue titled callback. So that'll be the name of our custom queue that we're going to be processing for. And then we'll just change the name of this scheduled item record here and make it callback events process, okay? And then I'll just do an insert and stay. Actually, before I do that, I do want to modify the repeat interval. Instead of waiting 30 seconds, I'll just want to wait 5 seconds. Make it a little bit more aggressive. I'll do an insert and stay to create, okay? So I just created that processor. So now that this job exists, every 5 seconds, the workers are going to check to see, hey, is let me run this job, okay? And then they'll process any events that are sitting in the event table that are associated with the callback queue, okay? So now that this is in place, we have all the pieces in place to do a test here. So, but before we can do that, we need to do one more thing, which is to modify our business rules so that it no longer does the callback itself, but simply fires that event so that the script action can do the callback. All right. So I've actually gone ahead and created a additional business rule, or a different version of this business rule right here. So I went and disabled that one, and this one I'm going to enable. And the only thing different here is I essentially commented out all the callback code, and I just added a gs.eventQueue function call at the end, specifying that callback function that we registered, the event registration, with the full event name here, which is the application scope.callback. That's being specified. And then the current glide record, which in this case is targeting the ECCQ table. So it's an ECCQ record. And I'm not using the other two optional parameters, but I am using the fifth optional parameter is to pass the name of the queue. So this is the name. The value that we want to pass here is the same value that we used when we defined our sys trigger record here. And in our job context field, we replaced that queue name with callback. So that should match. What we're passing there should match here, okay? So there you go. So this is in place. This is active. Now let's go ahead and do a test. We'll run the same test. We got 200 records that we're going to generate here. And this time it's going to use that eventing approach. So go ahead and click Run Script. All right. So it's generated the 200 events, the 200 API calls. Now I want to come to this event table and I want to take a look for queues that start with callback. And here we go. Here comes our events are coming in. We got 78 in there right now, and it's growing. It's at 127, so it should go all the way up to 200. So it's generating these events, and then as those are generated, then our job that we created, our systrigger job here, should be running to process those events. Let's take a look and refresh our system diagnostics page here and take a look at what's going on. So here we go. It looks like that job is running. The callback events process job has been triggered and it's currently running. It was triggered at 4:20:45. Yes, that was just about a minute ago or a little less. And let's refresh. So notice the difference here is that in this case, unlike the asynchronous business rule, it's only consuming one single worker thread. And what's happening is that this job is, when it kicks off, it's querying the events table for any event that has this matching queue name, and it's processing all those events in one job. So since each one of these events, each one of these callbacks that are going to be triggered in that script action is inducing a 20-second delay. That means it's going to be processing all 200 of these events sequentially, one by one, encountering a 20-second delay for each one. So 200 calls at 20 seconds to process each response is going to take about 66 minutes or so for a single worker thread to process all of those events in the single queue. So that is longer than I want to wait. That is not optimal. That is painful, right? So we need to be able to find a way to spread this out over more worker threads. But unlike the asynchronous job, we need to be able to have the ability to limit, how many additional workers we can consume, and that way we can leave some free for other critical system events to process while this slowness is happening. Okay, so that's the next step here. But yeah, so I just want to point out that this is good. This is a step in the right direction, but it's inefficient and it's way too slow to be of any practical use. So to take this further, the next thing we want to look at and do is we need to let's go ahead and move here. There's a couple things to keep in mind. We should talk briefly about event handling best practice, at least in my opinion, in regards to what we're talking about here. We should always strive to perform the smallest unit of work possible to quickly free up your worker resources. If you have a job that takes 20 seconds to complete, that's a long time to wait. You should look at ways of optimizing that code and figuring out why is it taking so darn long and trying to break it down, maybe even. And that's the other option is if you have a large job, maybe you're trying to do too many things at once, it's taking too long of a time. Think about breaking it down into smaller jobs so that you can get those events to execute and terminate fast, because the faster you can cause the event to terminate, the faster you'll free up that worker thread to be available to process other events in the system. So that's really the goal here, is you want to get it to execute. So if you have a large job, the longer it takes your script action to finish processing the transaction, the longer that worker thread is going to be held up. So, one approach might be to, have a script action insert a record into like an import set table, for example, without triggering business rules. And then on complete of that insertion, then you can fire another event that can do the slower processing and maybe rein it in so that it only can consume a limited number of worker threads. But if you have a large job, maybe you have an inbound API call that has like a huge JSON payload with 1,000 records that you need to update or something to that effect. Instead of trying to parse that payload and do a glide record for each one of those and update them all within the same job, instead parse the payload and for each record, put it in an object and fire another event. And the only purpose of that other event would be to take that object and insert it into an import set table, or update the target record with that object. So now you have, instead of one huge job that's doing a whole bunch of glide record calls and insertions, do one job to iterate over the big payload and fire a bunch of events, and then have those individual event jobs just responsible for updating a single record as quickly as possible. That would be my advice from event handling best practice. Then moving beyond, so we looked at how we were limited to a single job and a single worker with the revised approach. So now the way we can achieve scaling out and better performance here would be by manually going in and, just like I did this one time, creating more additional jobs within the system that can be picked up by other workers. So essentially, really all you have to do is come in and take this record that I just created, and maybe you would just change the queue name slightly to something else like this, and we can call it callback 1 or something, and then just do an insert and stay. And then so you'd have 2 jobs defined in the system that any worker can pick up at any given point in time. So, if you sent some events to the callback queue and then maybe the other half of them there and the other half to callback underscore one, then you can essentially split the performance across two workers when you do that. So my goal here is in my demo is I want to split these calls across a maximum total of 4 workers. Okay, but I don't want to have to go in and manually do this. And the tricky bit would be like if I created this by hand, how do I tell the event, or how do I know that I've already sent half of them to one queue and I need to send the other half to another queue, especially when they're coming back one by one in the asynchronous business rule. They have, one transaction has no concept of the context of the other transactions, or even that there are, 199 other transactions that are coming back at the same time or very shortly thereafter. So we need a clever way of being able to control the events and where they're going and where they're flowing and which queue they're going into. So my solution to this is that I came up with a way of writing a script include called auto scale event queues. Okay, and the purpose of this script include is essentially to pass in, or really it's just one function call that is the primary function call, which is give me a queue name. In other words, for each transaction that I'm processing, each event that I want to create, before I create that event, give me a queue name to throw that, to associate that event to, and is the ultimate goal of this. And so what I'm doing in this, and I'm going to go ahead and take this code out of here and put it into my IDE so I can walk you through it real quick. Let's just show you what it's doing. Here we go. Okay, yeah, I have it here. So what it does is on the initializer, so when you new up an instance of this script include, you want to pass in 2 parameters, optional parameters. One is the queue limit, which is the limit of how many events are allowed in a given queue before we want the system to automatically throw them into a new queue. Okay, and so I'm defaulting that value to 50 here out the gate, but it'll take whatever you pass in. And then the second parameter is the worker limit. So we specify this is the maximum number of worker threads I want to consume for this event. This is it. So don't go beyond this amount. So we pass those parameters in and basically just set them as local properties here on the script include object. Okay, and these are going to be used later in the code. So then the primary function that we're calling from outside of the script include is get queue name, and what it expects is a single parameter, which is just the string representation of the base queue name that you want to start with. In our case, we're using the queue name of a callback. Okay, so that would be the string value we would pass in here, and the goal and purpose of this function is to essentially go through and generate and check that queue name that I specified, and check to see, hey, does that queue already have, like, if the message or event limit is 50, does it already have 50 events in that queue? If so, then hey, automatically create me a new queue and throw this next event into that queue, until it gets to 50, and then rinse and repeat until the total number of queues are fully created, but limit the total number of queues that we create to the specified worker limit. And that is how this whole script is kind of playing out. So there's a number of functions in here, and so the get queue function is calling into is the queue at capacity function. So I'll just show you at a high level these functions. So we have validate queue job exists. We check if it's at capacity, a given queue's at capacity, yes or no. And this function uses these functions to check if the queue is over the limit and how many records are in that queue at a given moment in time. And then once it gets a response from that, there's this function here which does the validate that the queue job exists. So once to programmatically create a new queue processor, this is the code that does that. So we're setting a variable of job context, which is what we're going to store inside of the systrigger record that we're going to automatically generate here. But before we do, we new this up here. We set this variable like this, and we pass in our newly constructed queue name, and then we add that to this query here. You can see the job context is tacked onto the end. We do an encoded query against the systrigger table. If it's found, then the job's already there. We don't need to create it again, so we do nothing. Otherwise, we initialize our glide record and we set all these values. The name is just going to be the queue name. The job ID is hard coded to the run script job, and the state is 0, which means ready. Trigger type is 10, which indicates it's an interval trigger type, so it's recurring. It's a recurring trigger. And then we get the current date time object. We are going to add 30 seconds to it so that we can set the next action 30 seconds into the future. And then the job context we set to the variable, the job context variable from up top. And this is the script that's actually executing the process function against the custom queue name. And then last but not least, we set the repeat interval, which I have set to 5 seconds. And then we insert that job into the table. So this will automatically create our systrigger jobs for us up to the limit specified as the worker limit here that's passed in the worker limit variable. So it automatically will scale out our event queues by that function. So there you go. That's the gist of this script include. If you want to dig in deeper into the code, you're welcome to go check it out on the GitHub repository, which is posted in my video. So let me go ahead and demo how this works out and how this functions. Okay, so now that this script include exists to do all this magic for us, what we want to do next is modify our async business rule one more time. So, and to do this, I have a third version of the business rule that I'll just activate and show you what I'm doing in code there. Let me just go ahead and deactivate the second version. All right, let me close these out. And here is the last version of the business rule. So I'll set that to active. And what we got going on in here is now we're still doing that event queue at the end, except this time we're doing we're prepping and we're gonna use our auto scale event to get the queue name. So we're gonna start with our base queue name as callback. We're gonna set our event limit to 50. I want to limit to 50 events in each queue, and then we're gonna set our worker limits to 4. We only want to consume a maximum of 4 worker limits on the instance node, 4 workers on the instant node. And then with all these variables, we're going to get a queue name back by newing up an instance of our autoscale event queues object, passing in our initializer, the event limit, the worker limit, and then calling the function get queue name, passing in our base queue name here, and we're going to get back a more specific queue name, which is going to have a suffix of _1 through 4. It should be, since we're limiting it to 4. So it's going to be one of those. And then once that queue name's prepped, we'll just go ahead and do a GS event queue, calling our callback function, our callback event, right? Current glide record again with ECC queue. We're not using the second 2 parameters. And then the last parameter is our queue name. That's our custom queue name that we have. And we should have a job auto created if it doesn't already exist. For the queue name that we're given as a result of this function call. All right, so then that triggers that event. So this is active. Let's go ahead and run the test now and see what happens. Okay, so let's take a look at our system diagnostic. Let's see, this is probably still running. Yes, because as I mentioned, it was like 60 some odd minutes to run. So this has been running for quite a while, since 423 is now 436. So, all right, so I'm going to go ahead and terminate this job. But before I do, I have to clear out the events queues that haven't been processed yet. So let me come here and find all the ones that are empty, that have callback, right? Let me copy this, and I'm just going to do a little bit of cleanup before I get going. Put that there. And then this is going to be sys event. All right, let me go to a background script. Let me duplicate that out. And just double check to see what the current count is. 151 that haven't been processed yet. So we'll go ahead and delete those. All right, run. And those should be deleted. Let me double check. The count is now 0. Yes, count is now 0. Good. Now let's go to the active transactions on all nodes and see if that job's still running. Yeah, the callback events process is still running. So let's kill that job now that we've gotten rid of the events. There should be nothing for it to process. Let's refresh this. All right, that job has stopped. And we should be able to take a look at our diagnostic board here. And yeah, everything's idle now. Okay, so we're ready to run our next test. So we have everything set up. All we need to do is just re-trigger this call. This is going to be 200 again. And here we go. All right, 200 fired, 200 ECCQ records created. We should be seeing new events being created. Yes, new events are being created. It's incrementing, going up 98, 124. Okay, let's take a look at our system diagnostics page now. Let's see what we got going on. All right, let's see here. So I do see our async integration sensor is running presently. So it's should be calling that new function call to generate these new queues and what have you. And here we go. Here's our first queue that is started, our callback _1 queue here. Callback _2 has come into play. Callback _3 is now here. All right, looks like we're holding at 3 at the moment. Yes. Okay, let's take a look at what happened, and we'll take a look at the systrigger table here to see what we see. So now on the systrigger table, I want to look for anything that has the word callback in its name. Let's get rid of that. And here we go. So we have a total of 3 queues that have been created programmatically so far. I know I set the limit to 4. The reason why the 4th one hadn't been created is because in order for that to be created, you know, the last queue has to be have exceeded over 50 transactions for a duration of time, or 50 events, I should say, for a duration of time long enough for it to trigger the creation of the next queue. So since that didn't happen as of yet, let me trigger one more run of this and see if that'll push it over to 4. All right, so there's another 200 that I triggered, and we'll see what happens here. There's the 4th one that just got created. All right, cool. So now let's take a look at our system diagnostics page. You should see we still got 3 up there right now. So the 4th one is available to come in now. It's just a matter of one of the workers that are idle deciding to bring it in. Yeah, if we wait long enough, it should show up there. Oh, there it is, callback 4. Okay, so now we have success. We have achieved a limited number of consumed workers, a total of 4 to be precise, that are allowed to run and no more. And this is all being done automatically through that auto queue scale script include. Yep. So that's how you would go about doing this. So with this, you know, you can kind of have this approach is very effective. Is you know, from what I've seen, and you know, we're using it for everything. You know, anything that's doing an extremely large amount of API calls that you have to process in concurrency. It's really good for that, just to limit the impact on the instance. You know, just to rein it in and only allow it to consume a certain number of workers and no more at any given point in time. And then for slow jobs, for slow running jobs, maybe you only want to allocate, you know, a few workers to those slow jobs, but you want them to get done. But you don't want to starve system resources that are more critical to happen more immediately, as opposed to can suffer waiting for a little while. So this is the technique that that I use. And nowadays, whenever there's any sort of batch job that's being implemented, this is the approach that I encourage all of our developers to take in order to protect the system and take optimize performance, but at the same time protect the system from negative impact of all of the workers being accidentally consumed all at once. Okay, so now the last thing I would suggest that you could do to take this one step further to optimize performance even more is once you've run this and the system has generated the total number of queues uh, based upon the limit that you've specified. Now is a good time to come in to the systrigger records here and update your system ID value. If you select the system ID column for all of these jobs that were created, and you set this to active nodes, what the system will do, I'll show you here, is for every node in your instance, it's going to duplicate this job. So it's going to commit it to that specific node. So it's going to spread your jobs, it's going to create a copy of your job and spread it across all of your active nodes in the instance. Of course, this personal developer instance, there's only one active node in this instance, but in your normal subprod, you'll have at least 2, maybe 4. In production, you may have even more than that. So now because of this approach, you can enhance the speed of execution of these jobs significantly. I think let's see, I think I did have like some information on that. Let's see. Yeah. So like, for example, we were doing a test with 200 calls. So in our use case, with with the single node, we were able to spread out these transactions, 200 transactions, over a total of 4 workers. So, and we had a limit of 50 events per queue. So essentially, if you do the math on that, that's about 16 and a half minutes roughly to complete all of those transactions that would be running. So now if you imagine you had, 4 instance nodes available, and so you spread it out over 4, workers across 4 instance nodes. So that's a total of 16 workers. That actually cuts it down from, 16 minutes to 4 minutes, right? So the more, instance nodes you have, the faster those jobs will get completed because you can spread them out, evenly across all of those nodes. So that's a really useful last bit tip information there. Anyways, there you have it. This is what I wanted to share today, and I hope that it was very helpful and useful and eye-opening for a lot of people. And hey, if you got any feedback, any questions, any thoughts, if you think I misspoke on anything, let me know. I appreciate you and invite you to add a comment. And I hope you enjoyed this again. Take care, and we'll talk to you next time. All right, bye.